Don't use this microphone, your microphone.
Perfect.
That one.
Hello. Okay, great. Well, thank you to the second technical session. This one is on emerging applications. And we have our first speaker, who is Salman Jesse Uzuku. He's a PhD student from Newcastle University within our school, and is financially supported by the CDT in power electronics and sustainable electric propulsion. His research focus is on embedded AI-enabled battery state estimation, and is very interested in software development, machine learning, as you can imagine, and energy-efficient programming systems. I'll let you present.
Thank you very much. So today I'll be presenting on my work on AI-driven battery state of charge estimation using electrochemical impedance spectroscopy. I know there's a lot of interesting terms there that might be quite unusual to our group here, because I know a lot of us focus specifically on machine learning algorithms, but I will try and break things down, and I'll start with the motivation, the why, the kind of the background. I'll kind of set the scene. So as we all know, global warming has been a big issue in recent times, and a lot of countries have taken a big step to make the transport section more electrified, so electrification of the transport, and EV vehicles are big in contributing to this. A key part of this, when it comes to electrification, is understanding batteries, because we're now moving from a combustion-based engine to electric batteries. And this change is very important because we now need to worry about the power supply and the battery life and its longevity. So to efficiently kind of map this out and how to keep batteries in health, we have what we call a battery management system. The battery management system monitors a lot of the battery's health, going from the voltage, the current, the temperature, and it uses these things to manage the battery's thermal management. It manages the battery state, which is to do with the health of the battery currently, but also more futuristically. And it also helps in managing and limiting charge and discharge for more of a safety kind of purpose. And my work here focuses on what we call SOC, which is state of charge. The state of charge, what is state of charge? So state of charge can be seen as the remaining charge in a battery, or equivalent to what you'd say is a fuel gauge. Or if you pick your phone out and you look the top where it says 10%, 20%, that's what the state of charge would be. But obviously in our context, it would be for a car. In simple terms, this is 0% would be your battery is fully empty, and 100% would be you have a fully charged car and you can kind of drive. And it also gives you a good idea for drivers for how much mileage I can go. Because if you know how much percentage of your charge you have, then you can kind of say, I can drive for this long. So it's kind of useful in that context as well, because it helps to alleviate what is known as anxiety when it comes to mileage anxiety for drivers. So now, what is the current way that the state of charge is actually estimated? Well, there's indirect measurements, because you can't directly measure the state of charge, because it is a reference point from the nominal capacity to what is at your residual capacity now. So you can't directly measure this, but you can indirectly measure this and infer this using Coulomb counting, which is making use of the current. So you basically integrate the current over time, and this will give you the capacity. But there are problems with this method, because it's susceptible to initial errors in SOC, and it also has a buildup in errors throughout the process, because the more you drive and the more your battery gets worse, so the health of the battery gets worse, the SOC is very different, but this doesn't take that into account. The second method that's publicly used in cars currently is open circuit voltage, in which you imagine the voltage through the battery at a relaxed state, and then you map this to an SOC, and as you map it, you kind of have a truth table that kind of gives you what your SOC is for a particular open circuit voltage. But there's a big issue, because this issue is, for you to have an open circuit voltage, you need your battery to be relaxed. You need your battery to be in equilibrium. And this can't happen when there's a load or when you are driving. And sometimes to get this battery to actually become relaxed, it can take a very long time for resting. Sometimes as long as 10 hours, making it impractical for real-time systems. And another one, which is now probably the most used, is actually hybrid approaches, where you use both of these things in tandem, and you use both your voltage and your Coulomb counting to give you an idea of the state of charge. However, the same issues for individual ones persist. And you have this kind of system in which you have limited accuracy across various operating systems or operating conditions of the battery on the car. So that led to a new development in this idea of model-based estimations. You can break this down to basically say you take your battery, you model it on software, and you use this software model as your way of kind of deciding what your SOC is. There's kind of two current methods that are being researched. You have the physics-based models, in which you try and, obviously, as it says, infer the physics of the battery, and you use this to model the battery. As you can imagine, great accuracy, excellent. However, when you have physics-based models, you have this idea of a lot of partial differential equations that need to be solved, meaning it's at the far end of the computational time, and it takes too long to do in real time. And it's not practical, because now you can't use it in a real-time system, which a car would be. You have the other side of the spectrum, where we say, actually, let's take the battery and model it based on just its electrical form, or the electrical part of the battery as a circuit. However, this method, computationally quick, it's quite simple, it's very easy to interpret. However, you then let the same problem again now, where the accuracy is poor, because a battery is not just the electronics, it is the other parts of it, the ionic diffusion, it's all the physics part as well. So what's an easier solution? Why don't we say, we don't want any battery knowledge, but we want data, and we want to use this data to basically model our battery. And that's where I'll come to our solution, a data-driven modeling. This has been recently been researched in industry, and it has been shown promising interest for researchers, but also industry as well, because they've realized that as long as we can get good enough data, we can actually model the battery quite well. And also it means that our battery is subject to change as the data changes, which is a very important thing. But as mentioned, data is super important. And with data being super important, the quality and the quantity of your data matters a lot. Here comes this key term that I brought up as well, electrochemical impedance spectroscopy, in which what happens is you actually fire a voltage to the battery at different frequencies, and the response that comes out, which would be an impedance, is actually transformed using the Fourier transform to the frequency domain, and that gives you a Nyquist plot that you can use to actually model the battery. As you can see, for different SOCs, there are quite distinctive differences between the Nyquist plots, as you can see there. So this is actually quite interesting data that can be used for SOCs. However, now what is the key research opportunity? Where is kind of the place we fit ourselves in? Although this EIS has been used extensively for battery aging, which is to do with the health of the battery over time, it has not been used for SOC estimation. It's not been used or explored expressively for this problem. And then there's more need for research for MLs, how ML will perform with SOC using EIS. Comes to our two questions. Question number one, how will standard and emerging ML techniques perform for SOC estimation using EIS? And question number two, to mitigate the effects of limited available data, what an impact of feature propagations can we have by, what's the impact of feature propagation of EIS impedance on the model performance? So in other words, instead of can we take the EIS data and feed it to the model in different ways so that we can either augment the data across longer or to get better insights in simpler terms? So that comes to our project. First is the EIS data. We explore different effects of feature propagations. The next step then becomes the actual models. We explore a wide range of modeling, and we actually decided as well to actually split the problem into both regression and classification, because in a real system, you can see this as more regression, but in principle, a regression and classification are very similar things, but perform differently and give you different insights. So we explored a wide range of models, including obviously the settler machine, and then we have some performance analysis where we look and see how each model does and the practicalities about them. Now to the methodology. The data set was obtained from the work done by the group there and the reference below. And what they did was they took 4 Samsung batteries, cylindrical batteries that were rechargeable, lithium ion, because lithium ion is also the industry standard. And the experiment was repeated 6 times for each batteries. Before the start of the battery as well, each battery was recharged to the initial manufacturer specifications. And obviously, because it's only done on a short six times, you can assume that battery aging wouldn't have kicked in as much at this point into the process. And then what is then done? EIS is actually measured using a broadband measurement strategy for SOC values ranging from 10 to 100%, for 14 frequencies ranging from 0.5 hertz to 1 kilohertz. And these experiments then give you this kind of idea where you have six measurements on 4 batteries, 10 SOCs, and 14 frequencies, leaving you with 3,360 impedance values for you to use. And then obviously this gets doubled because you have your real and your imaginary when you deal with impedances. Now let's go to the data model, or how we call the feature propagation. There are 2 ways we could explore this. The first way was we can pass the full frequency sweep of the EIS to the model. So in that word, we have the real, and the imaginary for frequency 1, all the way to the real imaginary for frequency 14 passed in as a single propagation. And you standardize your data. And then for settler machine, this was booleanized using the quantile binning method, in which we bin the different, across the range of the features, and then these bins were then binarized and then booleanized to give you your booleans. And then these are passed through the ML models, and you predict your SOC. Or the second way is, actually, can we just learn from individual impedances and their frequencies what it's like? So in simpler terms, instead of taking the full sweep, we take 1 frequency. And taking this 1 frequency, we pass it through the model, and we standardize this and quantile binning, obviously, and then the model gives you SOC. With this method, your data is limited to the obviously 3,360. But with that model, now you times that by 14, and you have that much. So now you've enlarged your data size, and you have more things to work with when you are training your model. So the methodology is quite simple. All models were trained using MATLAB or Python. An Bayesian optimizer was used to determine the hyperparameters. As much as possible, I wanted to keep every model quite similar and not over-engineer any model to make them outperform any. So in the simplest form, every model is kind of in the same kind of states, and all models are trained in optimized for 300 epochs. And now we get to that results section, which gives us our key findings. So first one, experiment 1, which is when you have the full frequency sweep pass through. And for the regression, what we get is this right here, where you have all the different errors on the, you can see the mouse, get that across. Ooh, we have all the different errors, RMSE, MAE, ST, standard deviation, your max error. This is the standard deviation of the errors and your max errors. On this side, representing the bar chart, and on this side, you have your coefficient of determination, or the R squared, by this red line here. And then you have each model, so the LSTM, the artificial neural network, random forest, Gaussian process, the settler machine, kernel regression, linear regression, and SVMs. And this is the result. So as we can see, there's no underlying, the best was the LSTM, and quite by a mile. It quite superseded the rest in almost all the metrics, in fact, all the metrics. And if I get a close up into what the LSTM really looks like, you see that it's actually more in the magnitude of 0.1%. Obviously, with the SOC being percentages, then the errors are on percent. So with the errors being roughly between 0.1 to 0.4, and the R squared being practically 1, meaning it almost has a perfect fit. However, some reasons you could probably account to this is you can look at the idea that because the LSTM has a great focus on its on memory and looking back in time and its ability to learn dependencies across temporally, it was able to perform the rest. And however, this doesn't persist because obviously the sequence of data is very important. So if you reshuffle the data, the LSTM loses all its accuracy, but obviously that's expected because now the sequence is very different. However, for all the other models, they keep the same accuracy. And as you can see, ballpark in the middle, the settler machine does as well as kind of majority of them in the middle park. However, you also have to think we haven't specifically picked any new features. This is just a vanilla settler machine, and it still gives 6%, roughly 6% RMSE, which is still really good, and under 5% for the MAE, which is still really good and really competitive. And even away from just this experiment against other work that's been done out there, this is still also competitive with the average work saying 4%, 5% is what you typically get. So now the next step, which is the experiment 1, but for classification now, where we say that all the models are now put into their classes and not as a regression. You then get this kind of look where obviously now same again as the previous one, where you have all your metrics, the accuracy metrics that follow the bar chart here, and specificity, which is on this side. And as we can see again, a lot more models do better. A lot more models actually get practically 100% or 1 an accuracy, which is 100% in this context. That could be simply down to the fact that when the classes are more separated, they actually are quite easy to distinguish. But when you have a regression problem, you try and map these different classes into a fuller stream, which means that there's more chance of errors. But in this context, you have them in your classes and they're quite easy to distinguish. As you can see, artificial neural network, discriminant analysis, LSTM, and the settler machine are the best performers. And all the rest still do pretty well comparatively, with K nearest neighbor doing the worst in this context. Now, the next step with experiment 2, the regression model. We then have some issues. Well, it seems that the random forest is the highest performer, but you can see there's not a clear, especially when you come to these errors down at the bottom, there's not a clear separation between from here to about here. However, when you get to the discriminant and the coefficient of determination, which is a fit of the model, there is some clearer differences. And what we then gain here is actually, you look as well, you see that the errors are about 20%, which is not where it should be. So in other words, what we realized in this problem is that actually none of the models can really do this properly, meaning there are some similarities with a lot of the different SOCs when you try and actually model them this way, meaning there's some similarities with frequencies, but also across the SOCs that it means they can't be modeled this way. And this persists, although random forest is the best, this persists across the board, even when you get to the classification, where now you see over 40% accuracy, which is not great again. And it could just be, as I said, it is quite hard for the models to separate them. And with classification, the good thing we can do is we can actually have a look at how well it actually separates each model, each SOC. As we can see, a lot of the models can easily predict the 10%, but when you get towards the later end, it's quite harder for them to separate. About here, they're quite hard to separate this, to separate them and to learn them, meaning a simple truth could just be that there's not enough separation between models, especially in the similarities when you put them this way, that you might either need a deeper network, for example, for some models, or you might need something even more complex. So to quickly round up, what have we learned in this study? We have first proven that we have looked at how SOCs can be used, how machine learning can be used to predict SOC using EIS, both regression and classification. We have found some key findings that says that the full EIS sweep actually gives you a better fit of the data than splitting them across individual EIS frequencies. We have seen that LSTM outperforms others in a regression analysis. However, as I said, this is still quite preliminary in the context of not all models have been pushed to get the best out of them. And also the classification performance of a lot of models are really good because all the models pretty much, when you separate them by classes, can learn the differences between classes. The dataset used also was obtained with an online and onboard EIS measurements, meaning that this, in principle, could also be done in a battery management system, as long as these EIS measurements can be integrated with the system and your model can be fitted into the battery management system. Thank you very much. And if there's any questions, I'll be more than happy to answer them.
Thank you very much, Jesse. Is there any question? There?
So how hard is it to integrate some other factors other than this EAS? Like with the EAS, if I want to integrate a temperature or some other parameter, how hard will it be?
Okay, so already most battery management systems already have the standard voltage, current, and temperature involved with them. But EIS is like a separate thing. So the only thing would be you could integrate EIS, but also if you wanted to, you can integrate temperature to that as another parameter that might give it some more input. So it's not super difficult. The only difficulty would definitely be to figure out how the EIS itself can actually be integrated with the battery management system. I think for the temperature part, that would not be quite difficult. You would just have to train your model with temperature involved as well. But to integrate the EIS, there are some groups that are working on that part. Obviously, that's beyond the scope of what I do, but there are some groups that are working on integrating EIS with battery management systems, especially with SOC and SOH, because it gives a broader picture of the battery's current health, but also battery aging as well.
So more the parameters, more the prediction accuracy, right?
Yes, yes. In most cases, I have also done some other work, even though not presented here, where yes, the more features you add, or the more features that you can be put into it, the actual better your model will get. Yes.
Thank you.
Any other question? So I will say, considering the time, if there are no other questions, we can continue with the next talk. So.